Alright, let's now understand binary numbers, or base 2 numbers. Now, if you recall in the previous video, we said that everything we have in our computer is just zeros and ones. And well, what are zeros and ones? They are just numbers, right? So let's try to understand these numbers. Let's see what they represent. Now, we also said that these zeros and ones that we have different ways to represent them. Maybe using a transistor or a light bulb or a flash disk has its own system of saving these zeros and ones. So let's have an example. Let's put these boxes on our screen, and let's say that this is our own way of representing these zeros and ones. So they could be transistors, they could be light bulbs, we don't care, okay? So we've got these boxes, and in each one of these boxes we can have two different states. We can either have a 1 or we can have a 0. And again, this is the most basic thing that we have. This is the most basic unit that we have in computers. Now, each one of these boxes can hold 1 bit. So 1 bit, one of these boxes could either hold on or off, could either hold 1 or 0. Okay, so this is the most basic unit that we have in computers, that we have in digital information. Okay, the most basic unit. If you break it down, this is what you're going to end up with. Now, we also have another very common unit system in computers, and that's called bytes. And well, 1 byte is simply equals 8 bits. So if I take 8 bits and I group them together, I'm going to end up with 1 byte. So 1 byte is 8 bits grouped together. So these boxes, again, could either have two different states, either a 1 or a 0, and nothing else. We can't put anything else in these boxes. And again, each of these units, each of these numbers are 1 bit. So if I say that I have 1101, if I say that I have this amount of data, my data is 11 and 01, that's 4 numbers, and that means that I have 4 bits of data, okay? So now let's put some numbers in these boxes. So I'm gonna put maybe this number. We're gonna have 0, 0, 0, 0, 1, 0, and 1, 1. So we've got these bits holders, and now we have this amount of data. Let's try to investigate this, and let's see what this number exactly is. Let's try to understand this. What are these few zeros and ones in this particular combination? What exactly is this? Well, if we pull these out from the box, we're going to end up with this, which, well, is a number. So this is a number. And we call these numbers, again, binary numbers or base 2 numbers. And we're going to see in just a minute why we call them base 2. Now, right now, I have dropped the previous zeros, and you're going to see in just a minute why that's the case. And it doesn't matter if we add hundreds of zeros before our number, or we add in only 1, or we don't add any zeros. It doesn't matter, and you're going to see in just a minute why. So we've got this number. Let's see what this number represents. Again, this is just a number, but we were using a different system to represent the numbers that we were used to. So I could say maybe that I have 5 oranges. You can say that 5 number in zeros and ones, and the number that you're going to end up with if you convert 5 to a binary number is just some zeros and ones. So let's first talk about how we can get from a base 2 number to a base 10 number, to a number system that we're all familiar with. So if I say that I have this number, and I tell you to go ahead and calculate it and tell me what exactly this number is in decimal, what you're going to do is that you're going to take each number or each character and then multiply it by 2 to the power of its index. So we're going to have to take 1. We have to multiply it by 2 to the power of its index. Its index right now is 0, and the result is 1. We have to do the same thing with the second character from the right side. So we're going to take 1 again. Now we have to multiply it by 2 to the power of 1, and we're going to end up with a 2. Now we're going to take the third character, or the third number, which in this case is 0, and we're going to do the exact same thing. So let's take all the other numbers, and let's multiply them all by 2 to the power of their indexes, and here we can see all the numbers that we're going to end up with. So what we need to do right now is to take all these results and add them all together and we're going to end up with a number. And this number is a decimal number. It's a number that we are all familiar with. It's a number system that we all use. Now again, in the previous slides, we had a few zeros before this number, but as you can see right now in this formula, because we have to take each number and multiply it by 2 to the power of something, all these zeros before the first one will end up being a 0, because 0 times anything is 0. So we can just drop all these zeros before the first one that appears. Okay, very simple. So that's it about binary numbers. Okay, it's a simple concept to understand. It's just a numeric system that we only use 2 different numbers to represent numbers. So here my number is 1011. So let's say that I have a basket full of oranges. I could either say that I have 11 oranges in just the regular numeric system that we all use. A kid uses this numeric system, so it's very simple. We start from 0, we go up to 9, and then 10, 11, and so forth. Or I could say that I have 1011 oranges in binary. Okay, I'm using the exact same concept. I'm using the exact same number, but now I'm representing that number. Now I'm saying that number in binary instead of in decimal. I still have the exact same number of oranges. I'm just using a different system to say the exact same thing. Okay, these two are exactly identical. And this is what computers understand. They understand binary numbers. When they want to add two numbers together, when they want to do some operations, when they want to save something, they save them in binary. They save them in zeros and ones. And at each point, you can just convert that and see what you have in decimal, and that's pretty easy to do. Again, just like this formula that we have, you just have to take each number and then multiply it by 2 to the power of its index. Now, we call these numbers base 2 because, as you can see right now on my screen, we take each number and we multiply it by 2 to the power of something. So this 2 here, these 2's that we have here bolded, this is why we call them base 2, okay? So we multiply them by 2, and we also only have 2 numbers. So, therefore, we call them base 2. Alright, I want to also take a moment and talk about the concept of the indexes. We said in the previous slide that to calculate a binary number, we just take each number and we multiply it by the base, which is 2, raised to the power of its index. Now, what exactly is that index? Well, it's usually called index or position, and we start from the rightmost digit, and we assign that digit position number 0, and as we move to the left side, we just increment our position by 1, okay? So it's not like arrays, okay? It's not like indexes and arrays. It's just totally different. It has nothing to do with that concept. So our rightmost number is going to have the position 0, and as we move to the left side, we just increment our position or our index by 1. And then when we want to calculate it, we just take each number, we multiply that by 2 raised to the power of its position, which you can see right now, all the positions below the numbers. Now here we just got another binary number. In this case, we have 8 digits, so it's an 8-bit number. And also we call the rightmost number and the leftmost number something special. We call this rightmost number, we have a name for it, and that is our least significant bit, or LSB, or our least significant digit, LSD. Now, if it's binary, we can call it least significant bit, because in binary, each number is actually 1 bit. But if we were using hexadecimal or decimal, we can't just call the rightmost digit least significant bit, because that digit is for sure not just 1 bit. So in that case, we call them just simply least significant digit. Now the leftmost number here, we call this one our most significant bit, or our most significant digit, or MSB or MSD. Okay, so these are also the words that you're going to see a lot when you're dealing with binary and hexadecimal. Now, this should be pretty intuitive to you. I mean, if you just think about the math, why it is the least significant and why this is the most significant. Now, in this bit, we just have to take the number and multiply it by 2 raised to the power of 0, which is 1. And now, in this case, we have to take the number, multiply it by 2 raised to the power of 7, and that is 128. So if I just change this number here, if I just change this bit right here, I'm changing my whole number by 128 units. But if I change this one, I'm just changing my whole number by just 1 unit, okay? So as we move more and more to the left side, our number, our bits are getting more and more significant. And when we get to the end number is the most significant. So I also want you to know about these terminologies because we're going to use them sometimes, and just outside of this course and you want to deal with some binary and hexadecimal, you would probably hear these words a lot. And this positioning system is again the same thing with all the other numeric systems. So same thing in decimal, same thing in hexadecimal. We just take the rightmost digit, we assign that position 0, and by each digit that we move to the left side, we just increase our position by 1. So I just want you to know this because we're going to use the same concept in hexadecimal and also decimal for just a little bit in the next slide. So please keep this in mind. Now let's take a look at the number system that we all use, the decimal numbers or base 10 numbers. Now I'm just going to talk quickly about this because I want to make it clear to you why we call binary numbers base 2. So this is a decimal number. This 319 is just a regular number. Okay, this is something that you use all the time. We humans use this system, base 10. But let's see why we call it base 10 so that you would now understand better why we call binary numbers base 2. So if I use the exact same formula that I did in the previous slide, and I take each character and now multiply it by now 10 to the power of its index. So I'll take 9, and then I'll take 1 times 10 to the power of 1, which is 10. Now I take 3, and then times 10 to the power of 2, which is 300. And now, if we take all these numbers just like before, and we add them all together, we're going to end up with 319, which is the exact same number, right? Now in binary numbers, we only have 2 different characters or 2 different numbers, a 0 or a 1. And in decimal format, in base 10 number system, we have 10 characters. We have 0, 1, 2, up until 9. Okay? Now just like this, we can use many other numeric systems. We can have base 3 numbers. We can have base 4 numbers. Now let's say that we want to use a base 5 numeric system. In that case, we have to take 5 characters, maybe 0 up until 4, and then if we want to represent a number, we have to take each number and we have to multiply it by 5 to the power of its index to come up with a number that we are all familiar with. So just like that, we can use infinite number of numeric systems, maybe base 20, base 100, anything, okay? But in computers, we generally use 3 different numeric systems, either base 10, which is what we humans use, or base 16 numbers, or base 2 numbers. Okay, we're going to talk about base 16 numbers in the next video. But right now, that's it about binary numbers. Again, it's very simple to understand. It's just zeros and ones. And if you want to convert it into a decimal, you just take each character, multiply it by 2 to the power of its index, and that's it. Okay, it's very simple. All right, now that we understand binary numbers, let's now move on ahead and understand one more very important numeric system in the computing world, which is called base 16 numbers or hexadecimal numbers. So that's coming up next, and I'll see you in the next one.